slice of material part D has thickness T and the central maximum shifts up the screen to take the position originally held by the fifth order bright fringe, produced when no material was between the slits and the screen. Show the thickness of the slice is less than or equal to that. Okay, so if we know the thickness of the slice, we can work out, and we know its refractive index, we can work out how many wavelengths it's delayed by. Let's think. Maybe if we work from this equation, we might get somewhere. So that's our situation. Sine theta m plus x lambda 0 over d is our new case. Now what we're told is that theta is where it would be is where the fifth fringe would be. So where it was would be sine theta equals m lambda over d, where m is 5. So that's telling us sine theta is 5 lambda over d. Well, this is the old wavelength lambda 0. So 5 lambda 0 over d is that bit there. M in here, because this is a new case where the new central maximum has shifted from there up here. So m is 0. So we've got 5 lambda 0 over d equals x lambda 0 over d. That doesn't really tell us anything other than you've got 5 wavelengths. Maybe it does tell us something, because those are going to cross out. So x is 5, so it's going to tell me that when it comes out of here, it's been delayed by 5 wavelengths. Can I relate that to thickness? Okay, so you've got a material thickness T, and let's compare that case with air. So in air, here's our wave going through. Here, it's got 5 more wavelengths in it there. So we've got the speed of light, and here we've got speed and frequencies are the same. So C equals F lambda 0 for this case. So for this case, and that is f lambda nu, which is going to be our old speed f lambda 0 over n. So lambda nu equals lambda 0 over the refractive index. That gives us your new wavelength. Now what we want to show is that you're getting 5 delays. So in distance t, there are 5 wavelengths delayed. So the difference between lambda nu and lambda 0, so delta lambda is that, which is lambda 0 over n minus lambda 0, or lambda 0, 1 over n, take 1. That's your change in wavelength, and we're saying we've got 5 of those in distance t. So we've got 5 of those distances equals t. So we've got 5 lambda 0, 1 over n take 1 equals t. Gives me an equation for t. What does that come to? 5 times the old wavelength. 5, I think we're given that, aren't we? All the way at the beginning, 500 nanometers. 500 times 10 to the minus 9 times 1 over, is it 1.6 from memory? 1.6, take 1. What does that come to? 1 divided by 1.6. So it's going to be a number smaller than 1, take 1. I'll get a negative number, but I'm not going to worry about that. Iron number minus 3.3 times 10 to the minus 7. Doesn't doesn't correspond to 4.17 times 10 to the minus 6, that's for sure. Done that right, 25. So 5 times 10 to the minus 7 times 5, that's 25 times 10 to the minus 7. That will look about right. What's going on? Am I looking at this in too complicated a way? That's going to delay. Still think we should have 5 lambda and 5 times the difference. Five wavelengths. Not sure. Not quite sure where we're getting there.